So, module one revision, I'm going to scroll down to question 17. 17 is not difficult, but I want you to revise. There's a few things that I want you to revise just to make sure you have it in your head before you get into the exam. Yeah. So, a few quick definitions. An isotope has the same number of protons and a different number of neutrons, right? Same number of protons, different numbers of neutrons. We are going to use these questions as a bouncing board to revise the rest of the content. So if you notice I don't answer the question straight away or I keep asking you a few things, that's because we're not just doing this for the sake of the question. Yeah, we'll be revising a few things as we go. Okay, so 17, what's the atomic weight of some hypothetical element consisting of two isotopes, one with mass 64.23 and it's 26%, and one with mass 65.32, and the percentage is not given. Okay, they don't have to give you the percentages of everything. If you have two substances, they only have to give you the percentage of one. If you have three isotopes, they only have to give you the percentages of two. Why is that, guys? It's because one, two, and three, the whole thing in terms of percentages should add up to what? All of the percentages should add up to 100. Exactly. So what that means is if you know 1%, one of the percentages, you can figure out the other one. So there's only two here. The first one is 26, which means the other one is 100% minus 26%, which gives you, you don't need a calculator for this. Okay, good. I cannot tell. 74%. All right. When you're determining the atomic weight of an element consisting of a bunch of different isotopes, you go percentage times mass, and then you add it up for each isotope. Yeah, so this sigma symbol you saw when you were doing Gibbs free energy, enthalpy, and entropy. Percentage times mass for each isotope added up for all of the isotopes. Okay, so for the first isotope, they've given you 26%, which is, if I do that as a decimal, you get 0.26 times 64.23, that's the mass, plus 0.74 for the second one. We calculated that ourselves, multiplied by 65.32. And when you pop this in the calculator, you get 65.0366. So then your answer is D. Okay. You can get questions where they ask you to rearrange it the other way around. Question 18, naturally occurring rubidium consists of just two isotopes. One of the isotopes consists of atoms with a mass of da da da, the other mass of something else. And then this time they ask you for the percent natural abundance of the heavier isotope. So they're not asking you to solve for the mass now of the entire element, they're asking you to solve for the percentages, which means we're going to be rearranging the equation, okay? Again, guys, there are only two percentages here. They want you to get the percentage abundance of the heavier isotope, so I'm going to call that X, just like in maths class, you're solving for an unknown number. This is going to be X. And then, guys, if I'm doing this as a decimal, 100% as a decimal is what? 100% is just 1, yeah? So 50% is 0.5, 60% is 0.6, 100% is just 1. Okay, so this is X. They together have to add up to 1. Okay, so the percent of the other one must be 1 minus X. Yeah? And then you just pop it into your calculation again. So 86.901 for the heavier isotope multiplied by X plus your lighter isotope 84.912 multiplied by 1 minus X. And guys, they haven't given you the mass of the actual element. Okay? That's fine though, because where do you normally go looking for where do you normally go looking for the mass of an element? Guys, so we said the two elements together add up to 100%, right? So whatever it is, so the percentage for, I don't know, isotope 1 plus the percentage for isotope 2 is equal to 100%, which we said is equal to 1 if you're working with it as a decimal. So if one of the isotopes is X, the other one is 1 minus X. Yeah. They add up to 100% or they add up to 1. So if one's X, the other one's 1 minus X. Exactly. You normally go looking at the periodic table to figure out the molar mass, to figure out the mass, yeah? You're used to questions having already given it to you in the question. Just keep in mind they don't have to do that. If they specify the element, you can go looking for it yourself. What is the molar mass of rubidium? What is this equation on the screen supposed to add up to? Rubidium. 85.47. And guys, all you're doing now is moving this around. Yeah. So we're doing 86.901x plus, I'm just going to expand my bracket. So 84.912 minus 84.912x is equal to 85.47. Okay. These two get grouped together. Don't let the maths confuse you. These two get grouped together. Can you do that subtraction for me? What do you get for that? Plus 84.912 is equal to 85.47. So collect the like terms. When you do that first x minus the other x, what's the leftover? 1.989x. Thanks, guys. And then all you're doing now is moving it around to solve for x, yeah? So 85.47 was on the right. I just keep it on the right. I bring my 84.912 over. It was a plus on the left, so when I bring it over, it's a minus. And then I divide the term with the x out, so 1.989. And then what do you get for x? Point. These two, we were collecting the like terms. So this is now a maths question. I'm just solving for x. Those two both had x. I just subtract them from each other because one's minus the other. That's the 1.989 result. 0.2805. And then guys, we worked with this as a decimal. Yeah. So instead of 100%, we did 1. So 0.2805 as a percentage is 28.05%. Yeah. So I do my calculation in terms of decimals, and then they normally express it in terms of percentages. So your answer here is going to be B. Okay? So straightforward, your isotope calculations are straightforward. It's just I want to make sure you have this in your head before you get into the exam. Yeah? 19 might be a bit confusing. Okay? So when I start saying stuff like that, this is your sign. I've told you before, if it gets too much, then you pop your pen down and your priority is to understand the content. This is recorded. This will be up. Okay? Question 19. Let's read this together slowly. The first ionization energy of an element is the energy required to remove an electron from a gaseous atom of the element, and this is the equation, yeah? So keep this in mind. If you get challenging questions that are like, how is first ionization energy measured? What's the standard test for first ionization energy? I need you to keep in mind it's a gaseous atom. Yeah, that's how they do the test. Otherwise, you won't be able to compare it with other elements, okay? For our sake, though, in terms of answering this theory question, your only concern is this part, your energy required to remove an electron. Okay, so let's dissect this and keep it straightforward. First ionization energy is the energy required to remove an electron. What that means is if the FIE is really high, first ionization energy, if it takes a lot of energy to do it, guys, in simple terms, what it means is this. Yeah, if the first ionization energy is high, in simple terms, what it means is it's hard to get rid of an electron. That's pretty much it. If it takes you a lot of energy to if it takes you a lot of energy to do something, it just means it's hard to do. What it also means is the element likes to keep its electron. If it's hard for you to pull it away, it means it likes to keep it to itself. Yeah. Likewise, vice versa, if the FIE is really low, it's easy to get rid of the electron. So just keep this in mind when we go to answer the question, okay? The values of a few first ionization energies for the third row elements are shown in the graph below. Third row is a period in the periodic table. What is a column in the periodic table? The rows are called periods. The columns are called, starting with the G, the columns are called groups. Good. All right. Which of the following reactions is exothermic? And then you get a bunch of this. Okay. Module 4 revision as we go. What does it mean to be exothermic? Means to release heat. Okay, good. Now, here's the thing. I need to train you on how to figure things out in the exam because there will always be new questions that don't show up. Yeah. We we need to develop an ability to see how different parts of the syllabus go together. Yeah. So this next part, I'm gonna get you to control the conversation. We need to see how the fact that it's exothermic relates to this idea of first ionization energy from module 1. Yeah. Releasing exothermic means it releases heat, which means it's releasing energy. Heat is a form of energy. Heat is thermal energy. Yeah, so we're sort of getting there. We're getting back to the whole first ionization energy idea. If you're releasing heat, if you're releasing energy, the system has lost or gained energy. Okay, systems lost energies. Energy has been lost. Does the idea of energy being lost remind you of anything you learned in Mod 1? Before I give you any hints. Maybe I'll rephrase it. Yeah. Instead of energy being lost, I'm aware you didn't hear the word lost in year 11. You did hear another phrase in module 1 though. You heard of um low energy. Okay. When we talked about energy in mod 1, we never really talked about losing energy per se. We talked about having a lower level of energy. Does this ring a bell? Lower energy is more or less stable. Energy shells, yes, that's one thing. Energy shells isn't the idea of energy shells itself isn't relevant here, but we're on the right track in terms of thinking about energy, yeah? So we're not going to talk about energy shells here, but we did apply the idea of energy with those electron shells. Guys, when the electrons were at a lower energy level, okay? When the electrons were at a lower energy level, how did you describe that? Was it more stable or less stable when it was at a lower energy level, those electrons? It was more stable. Okay, good. In module 1, when we talked about energy levels, when we talked about electrons, we said the lower energy level is more stable. All right. So the actual idea of the electron, I'm not concerned with. It's not relevant here. But the way we talk about energy applies here as well. Okay. So guys, what I want you to keep in mind is this: an exothermic reaction releases heat. Your system now has less energy than it did before. It's more stable. Okay. What does that have to do with these 4 types of reactions, though? Do we like or do we not like more stable? We like more stable. Okay. We prefer or we like things to be more stable. All right, now next question is this, yeah? If it's more stable, if it's something you like, if it's something you prefer, as a person, let's do an analogy first before we apply it to chemistry. If you're in a situation that's more stable, are you doing something you want to do or you're doing something you don't want to do? If you're in a situation that's more stable for you, are you doing something you want to do or something you don't want to do? Something being more stable probably means you're doing something that you prefer to do, yeah, that you like to do. All right, now that's the analogy, okay? The event that we're trying to figure out here is ionization energy. The situation here is whether or not it likes to get rid of an electron or whether or not it doesn't. Okay, so guys, putting two and two together, yeah, ionization energy, it's about whether or not you want to get rid of your electron, you want to keep it. Yeah, we've already said the reaction that's exothermic, the reaction that's more stable, being stable means you're doing something you prefer to do. Okay, it might be a reaction, it might be losing electrons, it might be gaining electrons. In this case, it's about losing electrons. Okay, so now applying the analogy to a chemistry context, whichever reaction is more stable has to be the one where the element that would rather lose its electron actually does lose its electron. Okay? This is the situation that's going on here. We said exothermic, more stable, doing something you like to do. So the answer to our question, it could be, like I said, it could be concentration, it could be collisions, whatever. In this case, they happen to be talking about losing electrons. The one that's more exothermic, the one that's stable, has to be the element that would rather lose its electron actually does lose its electron. It's doing what it wants to do. Okay, now relate this back, okay? Because now at the moment we're only talking about this conceptually. I have to relate this back to the graph, okay? The element that would rather lose its electron. The graph was about first ionization energy. The question is this, the element that would rather lose its electron, is that the one that has the lower first ionization energy or the higher first ionization energy? The one that would rather lose its electrons. Okay, the lower FIE. All right, cool. Now, let's go back and have a look then at these four options. You have a few different cases. You've got you've got chlorine, aluminium, phosphorus, and sulfur. Yeah. Those ones are going to be changing, which means if I can look at something that stays the same the entire time, it would be a lot easier. Yeah. Magnesium is the one that's staying the same in all of them. Okay, so it's going to be easier to think about it in terms of magnesium. In all of the cases, magnesium went from a plus to a zero. Think about what an electron charge is. An electron is negatively charged. Magnesium went from plus to zero. In all of these four options, did it gain an electron or did it lose an electron? Okay. In all of these cases, magnesium gained an electron. Yeah, because plus one minus one will give you the zero. Okay, magnesium gained an electron. The element that would rather lose its electron actually does lose its electron. Vice versa, the element that would rather gain an electron actually does gain an electron. Yeah? So you can talk about it both ways. You can talk about the one that wants to lose, you can talk about the one that wants to gain. In this case, magnesium in all four cases is gaining an electron, so I'm going to use this second one just because it's easier. Yeah, otherwise I have to keep thinking back and forth. Okay, magnesium's gaining an electron in all cases, so I'm going to do it this way. Okay. You guys told me that the element, if it prefers to lose an electron, it has the lower FIE. If it prefers to gain an electron, it has the higher FIE. Okay? In all four cases, magnesium is gaining an electron. For it to be doing what it actually wants to do, it needs to be the one in the reaction to have the higher FIE. Yeah? For it to do what it actually wants to do, it needs to be the one with the higher first ionization energy. All right? This is magnesium. Chlorine, option A has chlorine, option B has aluminium, option C has phosphorus, and option D has sulfur. We said for magnesium to be doing what it wants to do, which is gaining an electron, it needs to be the one with a higher FIE, which means the other one has the lower FIE. Magnesium has the higher energy, the other one has the lower energy. Which one's your answer? Magnesium, guys, magnesium needs to be the one with the higher energy. The other one has to have the lower energy. Good. Your only answer here is going to be aluminium. Magnesium is higher than aluminium. In all of the other cases, the other elements have a higher FIE. They would prefer to gain an electron. Okay? So guys, B is exothermic, which means all of the other ones are what? If they're not your answer, all of the other ones aren't exothermic, which means they're endothermic. Good. The other ones are less likely to occur. Okay? All right. So this is not the kind of question that you memorize. The questions will change. What I want you to keep in mind generally that you can apply to different questions is this. Okay? Because this idea can be applied in a bunch of different ways. I need you to remember that more stable means that there's less energy, and we prefer that. Yeah, we like things to have less energy. That's more likely to occur. So apply that to whatever situation they're referring to. Okay? Question 20, which of these isoelectronic species has the smallest radius? Isoelectronic means that it has the same electronic configuration. And guys, electronic configuration depends on the number of electrons. Yeah? So same electronic configuration also means same number of electrons. Okay? Isoelectronic means it has the same electronic configuration. So if you do the SPDF notation, or if you do the orbital diagrams, or if you do the noble gas notation, you'll get the same exact answer for all of them. It also means that it has the same number of electrons. Which one of these has the smallest radius? The radius depends on how far your valence electrons are. And guys, what's holding on to your electrons? What affects whether or not your electrons are really far away from the nucleus or really close to the nucleus? Yes, it is the nucleus, but I want something a bit more specific. What's in the nucleus? Because it's not the entire nucleus that holds on to it, it's the number of protons. Good. Well done. So the protons in the nucleus have a positive charge. It holds on to your electrons outside, which means the radius depends on the number of protons and the number of electrons. That's what we have to compare for these four options. Okay? The number of protons is its atomic number. So look at your periodic table for me. What number of protons does SR have? Sr has 38 protons. That's where it is in your periodic table. And then guys, if it was neutral, the number of protons and the number of electrons would be the same. Yeah, if it's neutral, it will be the same. A 2 plus charge means that it lost 2 electrons. So it should have 38, like it does have 38 protons. But if it's Sr2 plus, it lost 2 electrons. How many electrons does it actually have then? 36 instead of the 38. Rubidium, Rb, how many protons from the periodic table? 37. It only lost 1 electron. It's a +1 charge. Number of electrons is also 36. Good. And then Se, protons, 34. And then a 2 minus charge actually means that it gained 2 electrons. So 34 plus 2 will give you a 36 electrons as well. Exactly. Okay, good. Which one will have the smaller radius? Which one has the most power in the nucleus to pull your electrons in? Which one has the most power in the nucleus to pull your electrons in? It's going to be A because A is the one that has the most number of protons. They all have the same number of electrons. A has more protons. It has more power to pull those electrons in. So your answer is going to be A. Good. So D is not your answer because it doesn't just depend on the number of electrons, it depends on the number of protons as well. Okay? All right. Remember, any questions as we're going, let me know. 46. Bromine, strontium chloride, and iodine monochloride have similar molar masses. Suggest with reasons the order of melting points for the three substances. When you get asked to explain different properties in Module 1, I need you to keep in mind that with melting point or with boiling point, it depends on the strength of the forces. You need to know what you're actually talking about with the different properties, yeah? If you get asked about melting or boiling point, it's about the strength of the forces. If you get asked about solubility, it's about having the same forces. Okay, it doesn't matter if it's strong or weak. If they're both weak dispersion, that means it's soluble. Okay, it's about having the same forces. And who remembers with electrical conductivity what you need for that? I gave you 2 criteria for that one when we did it in Mod 1. You need something that has, starting the CH, you need something that's charged. And number 2, it needs to be able to, starting with an M, needs to be able to move around. Good. Guys, electrical conductivity, you need to have charge, and you need to have charge that's able to move around. Okay? So adjust what you talk about depending on what they ask you for. In this case, they've asked you for melting point, so we're going to talk about the strength of the forces. All right. You have a few different kinds. They both start with I. What are the 2 different types of forces? Intermolecular and intra. Good. Intermolecular and intra. Okay. Now, you need to know what kind of forces you talk about depending on what the chemicals are in the question. Guys, with intermolecular forces, that's only for covalent molecules. Okay? Intermolecular forces exist between molecules, which means your chemical has to be a molecule in the first place. Intramolecular, anything that's a network. Okay, so if you ever see an ionic network, a covalent network, a metallic network, you will always be talking about ionic bonds, covalent bonds, metallic bonds. I should not be hearing you mention weak dispersion, dipole-dipole, or hydrogen bonding. Yeah, the ones that are a network are ionic compounds, metallic compounds, And for covalent networks, there are only two examples in the syllabus for covalent networks. What are they? One starting with a D, shiny, jewelry, diamond. Not graphite. Graphite is an allotrope of carbon. And then one starting with an S, silicon dioxide, SiO2. Good. Okay, these are your only options for covalent networks. If you see something covalent and it's not one of these two, it's going to be a covalent molecule. So covalent molecules is everything else. Yeah. If it's not ionic, metal and non-metal, if it's not a metal, if it's not diamond, if it's not silicon dioxide, then it's a covalent molecule. Covalent molecule is everything else. Yeah. So if you see these three, you talk about breaking the bonds, ionic, metallic, covalent. If you see this, you talk about, I don't know, weak dispersion, dipole, hydrogen bonding, depending on what you figure out. Yeah? Okay. So your issue with these questions is just going to be deciding what you talk about anyway. And then once you figure that out, the rest of it becomes easy. Yeah. So you've got three options. You've got bromine, you've got strontium chloride, and then you've got iodine monochloride. Guys, bromine is non-metal with non-metal, ionic, covalent, or metallic. Non-metal with non-metal. It's covalent, and then I gave you your options for covalent networks and covalent molecules. Bromine is covalent molecule or covalent network. It's a covalent molecule. Covalent molecule. Which means, what are you going to talk about when we go to melt it? Are we going to talk about intermolecular forces, or are we going to talk about breaking the covalent bond between the two bromines? It's a molecule. What do you talk about? You talk about the intermolecular forces. Good. Guys, bromine is bonded to another bromine. Any room here for it to be polar, for the electrons to be pulled in different ways? It's the same element, so it's not going to be pulled in different ways. So therefore, it's non-polar, exactly. And if it's non-polar, the only intermolecular force it forms is weak dispersion forces, which requires low energy to break. So therefore, low melting point. Okay, let's skip to iodine chloride. WDF is weak dispersion force. Let's skip to iodine monochloride. Ionic, covalent, or metallic. Iodine's a non-metal, chlorine's a non-metal, so it's covalent. But guys, these are two different elements. They're not the same one. The electrons might be pulled differently. So you're going to tell me it's polar or non-polar? It's going to be polar because you have two different elements that pull it in different directions. They don't pull the electrons by the same amount. So it's going to be polar, which means everything forms weak dispersion forces, yes, but it also forms dipole-dipole forces as well. DDF is dipole-dipole forces. So therefore, it requires slightly more energy to break, which means it has a slightly higher melting point. And then guys, you've got SrCl2. Strontium, Sr is a metal, chlorine is a non-metal. This is no longer covalent, this is now ionic. And guys, if it's ionic, you don't have different options for the structure. There's no ionic molecule. It's definitely going to be a network, which means when I go to talk about melting it, I don't talk about in weak dispersion, dipole, or hydrogen bonding. What am I breaking when I'm melting an ionic compound? What kind of bonds if it's an ionic compound? It's an ionic bond. Good. So to melting requires breaking the ionic bond, which, guys, bonds require way more energy to break than forces do. Yeah. These are the things that actually hold your atoms together, that keep the formula. So if you're going to break the ionic bond, it requires lots of energy to break. So it's got the highest melting point. Okay. So they asked you to order it. That's why I did it in a different order to the question. Bromine's lowest, followed by ICl, followed by SrCl2. Okay. So again, when we do revision, you don't want to have the actual answers to a specific question memorized. You need to know what generally you can take away. This is the stuff you take away to apply to any kind of exam question that you get in addition to this. Yeah, and then you apply the general stuff to a specific question like we did here. Okay. All right, good. That's your module 1 done. Take a quick break. 7:33, we'll come back. We're going to start module 2, 7:33. Hydrogen gas reacts with 5 liters of nitrogen gas under constant temperature and pressure conditions to form 10 liters of ammonia gas. What is the minimum volume of hydrogen gas required to produce this amount of ammonia? I've told you before that when you're doing stoichiometry or you're dealing with ratios in a balanced chemical equation, you always do that with moles, with one exception. Yeah. Stoichiometry works with volume if everything in the equation is a gas. Stoichiometry works with volume if everything in your equation is a gas. This is because of one of the laws you learn in your first inquiry question for Module 2, which is the law of combining volumes. Okay? Your law of combining volumes tells you that if you have constant temperature and pressure, at constant temperature and pressure, gases react in, gases react in simple whole number ratios by volume. Okay, so the law of combining volumes is basically saying what I just told you. If you've got a gas, the volumes are in ratio, okay, in stoichiometric ratio. Yeah. So things like, oh, multiply by the number you're trying to go to, divide by the number you're getting away from when you're looking at the coefficients in an equation. Do that for moles is how you normally do it. You can do it for volume as well if everything is a gas. As mentioned here, hydrogen gas, nitrogen gas, ammonia gas. Okay, so our only job is to write the equation out and figure out the ratio. You've got H2G, because remember, hydrogen's diatomic. You've got N2G, nitrogen's diatomic. And then who remembers what ammonia is? I've told you this so many times. Ammonia is NH3, yeah. Ammonium ion is NH4 plus. Ammonia is NH3, two different things. Okay, so attention to detail is needed for this formula. Ammonium ion, NH4 plus. And then I need to balance it, otherwise the ratio doesn't work. I've got a 2 here, and then I've got a 3 here. Yeah? So guys, you've got, the question told you 5.00 liters of nitrogen, and then they've told you 10 liters of ammonia. Yeah, remember, multiply by where you're going, divide by where you start. So if I let's pick nitrogen, if that's what you want to do it in terms of, you're going to the 3 for the hydrogen, so you're timesing by 3, and then you're getting rid of the 1 in front of the nitrogen, so you're timesing 3, divide by 1, do the same thing to the actual number, and then you'll get 15. Okay? If you don't want to do it in terms of nitrogen, and then you, I don't know, they've given you two numbers, so you want to do it in terms of the 10 liters for ammonia instead, you're going to the 3 for the hydrogen, so you're timesing by 3. You're getting rid of the 2 in front of the ammonia, so you're dividing by 2. Do the same thing to the actual volume. The 10 liters for ammonia times 3 and 2 will also get you the 15. So either way, your answer for the hydrogen gas is going to be C, 15 liters. Okay? So key takeaway from this question, anytime you see a reaction in your exam, that's all gases, and they happen to give you volumes, use ratio work with that volume. Yeah, you don't have to convert it to moles, it'll be proportional. Okay? All right. Good. Question 3. How many hydrogen atoms are in 2.5 grams of pharmacolite? And then whatever that is. And then luckily they've given you the molar mass, which is good because that's way too long for us to calculate. Yeah? Key learnings from this question that you want to apply when you get into your exams. Ratio work, with the exception of this, guys. So I'm going to ignore that now, okay? Ratio work, with the exception of gases and volume, ratio work is always done in terms of moles. Okay, with the exception of that law of combining volumes that I just told you about, but we're done with that now. We're going to deal with every other case because that was only one case. And then, guys, when I say ratio work, what I mean by ratio work is relating atoms and molecules. Yeah, because in a balanced chemical equation, you're relating the molecules and there's the coefficients, the ratios in the balanced chemical equation. There's subscripts in a formula that tells you the ratios between the atoms in one molecule as well. So when I say ratio work, I'm saying you're relating the atoms and the molecules to each other. Okay? It's always done in terms of moles. Now, what that means is this, yeah? When you go into the exam and you're doing reading time, okay? Questions that mention different formulae. Step number 1 is to convert to moles. Okay? Doesn't matter what they're asking you, doesn't matter what the formula is, doesn't matter what the two different types of formulae are. You don't know how to get to the other element unless you have moles to begin with. Yeah. So step number 1, ignore whatever element they're even asking you about. You have to get to moles first. Okay. So in this case, I've identified they've asked you for hydrogen, but they've given you pharmacolite. When I mean different formula, I mean like one is H2O and the other one is NH3 or something. Two different chemical formulae. So they've given me pharmacolite in question 3, and they've asked me for hydrogen. Those are two different things. Don't know how I'm going to get to hydrogen yet, but step 1, I need to change the 2.5 grams into moles in the first place. You have a bunch of different equations to get to moles. If they've given you mass, what formula are you going to use out of all of the ones that you have under your belt? If they've given you mass, the formula you're going to use is mass on molar mass. So we're going to go 2.50 grams, and then in this case, they've given you the molar mass, so 216.0 grams per mole. What do you get for the moles of pharmacolite, please? Point 0.01157 mole. And then guys, when you're going, let's say I told you that you had one NH3 molecule. How many hydrogens are in here? 3. Okay. If I told you that I had 3 NH3 molecules, how many hydrogens would there be in here in total? For 3 molecules in total, 9. And then if I told you I had 5 NH3 molecules, how many H's would you say I have? 15. What are you doing to get from here to here each time? What operation did you do? Or like, did you times, did you add? You times by 3 each time, yeah? And then guys, numbers in front of a formula in a balanced chemical equation are called coefficients. What are the little numbers on the bottom right of things? Numbers on the top right are called superscripts. Numbers on the bottom are called subscripts. Good. This is a subscript. Okay. So this is your general takeaway to apply to different exam questions, not just this one. When you get asked about a molecule and you're trying to go to an atom in the molecule, multiply by the subscript. Okay. Which means, guys, the other way around, if you get given the atom and you get asked for the molecule instead, you're not multiplying. What are you doing in that case? You're reversing the operation, which is now a division. Exactly. So guys, if you're going molecule to atom, multiply by the number of atoms, multiply by the subscript. If you're going atom to molecule, divide by the subscript. Okay. Now, subscript is what tells you the number of atoms. I'm going to do a little bit of a note here. What I actually want you to multiply or divide by is the total number of atoms. Okay, what I actually want you to multiply or divide by is the total number of atoms. I just say subscript because usually the atoms are only in one spot, so you can just look at the total subscript. Sometimes they break it up. Yeah. So I'll give you an example. Like if I gave you CH3COOH and I asked you about the hydrogen, guys, hydrogen shows up in two spots here. Okay. So you can't just look at the subscript 3. What I want you to multiply by or divide by is the total number of atoms. So 3 plus this little 1 is actually 4. There's 4 H's total in CH3COH. Okay, so I'm just saying subscript for simplicity. Yeah? Multiply or divide by the total number of atoms, especially if it shows up in different spots. Okay, so we're going to take this. This is your general takeaway. We'll apply it to this question now. The formula is CaHAs O4.2H2O. All right. Guys, there's a H here. And the way you read this thing on the right is there's a water molecule, there's a H2O, and there's 2 water molecules. If there's 2 water molecules, how many hydrogens in total coming from the water? There's actually 4 hydrogens in total coming from the water, plus the extra hydrogen on the left of that dot, guys, means how many hydrogens in this formula in total? 5. Okay, good, 5. So 2 hydrogens per water, 2 waters in total means 4, plus the one on the left means 5 H's total. In this case, they gave me the molecule. They are asking me for hydrogen atoms. So I'm going times the subscript or times the total number of atoms. Yeah. So the way you write it is you go, oh, moles of H is 5 times the moles of pharmacolite, which is 5 times 0.01157 dot 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 mole. And then once you've got the moles of the chemical, do whatever conversion you want, okay? So I'm going to make an extra star here for your notes. Your first job is to get to the moles of the chemical in question, which basically means the chemical they're asking you for, okay? Okay, your first job is to always get to the moles of it. Okay, once you've done that, then convert to whatever variable they want, whatever variable the Q asks for. Okay, go moles first, then whatever they ask you for afterwards, not the other way around. Okay, moles first, then whatever they ask you for afterwards. All right. They've asked you for the number of atoms. This formula isn't in your data sheet. Okay, so you get mass on molar mass, you get CN on V, you don't get this one. Moles is number over Avogadro's number. What's Avogadro's number? A dozen is 12. Avogadro's number is? You get Avogadro's number in the data sheet, by the way. You just don't get the entire formula. Yeah, good. 6.0, well done. 6.022 by 10 to the 23. So it's in your data sheet. Sometimes fiddling with your data sheet makes you a bit nervous though, like if you can't find it and you don't want to have to go out and look at something else. It messes with your focus, yeah? So it's good if you have it under your belt. 6.022 by 10 to the 23. They want the number of atoms. So we're solving for big N, yeah, which means I'm multiplying that Avogadro's number out. So big N for H is lowercase n moles times Na. What did you get for the moles of H earlier? So your moles of pharmacolite was your 0.01157. I forgot to ask you for the moles of H. Point 0.0578-ish. And then we'll pop that into our last one where you do multiply by Avogadro's number. So 0.0578 times what you guys told me, 6.022 by 10 to the 23. And then what do you get for your final answer, which is going to be where we pick our option? So 3.48 by 10 to the 22, which gives you D. Good. Well done. Any questions as we're going, let me know. Okay. Question 5. A mixture of K2S, K2SO3, and K2SO4 is found to contain 60% potassium by mass. What is the mass percentage of oxygen in the mixture? What did you learn from the previous question? They've given me 60% for potassium, but they're asking me for oxygen. What variable do I need if I want to jump between different chemicals and different formulas? What did you learn from the previous question? Anytime you notice they ask and give you things that are different, your first job is to calculate what? Your first job is to calculate moles. Good. They haven't given you a number in terms of moles. They've given you a number in terms of percentages, but it's percentage by mass. So I have a little bit of wiggle room to get to mass eventually, yeah? If you can recall a little bit of your empirical formula, guys, you can set whatever mass you want for the entire mixture because anytime you multiply by a percentage, it'll like be in proportion, yeah? So like if one's 60% and another's 30%, when you multiply by a number, it'll be in ratio after that, yeah? So if you've got a percentage, what's the easiest mass to set? It's just going to be 100, yeah. Because guys, if you do 100 for the whole thing and then you times by 60%, what's the mass of just the potassium? It's going to be 60, exactly. So you can set whatever mass for the entire thing you like, but I'm going to set 100 grams for the mixture. you can set whatever mass you like because when you multiply it by the percentage, it'll still be the same 60%. Yeah. It's just that 100 grams is easy because when you multiply by the percentage, you'll get 60 grams. Right. So your mass of potassium is 60% times 100 grams. It'll give you 60 grams. So my first job is to get this to moles of potassium is equal to mass on molar mass 60 grams, and then potassium is 39.10 grams per mole. What do you get for the moles of potassium? Thanks, guys. 1.5345 dot 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 mole. So if you get an equation, a balanced chemical equation, you look at the coefficients. If you get a formula, I told you to look at the subscript, you multiply by whatever the subscript is if you're going to the atom. Your only issue is, though, you get three different formulas. My question for you is this. You see this question in the exam, you know your general idea. If you're going from element to another element, you look at the subscript. What subscript are you taking? We will be taking a subscript, by the way. We will be looking at the ratios. I'm just asking you which one you're going to take. And then if you can't give me an answer, let me know what concerns you have at the moment, and then we'll figure it out as we go, yeah? So I'm asking you what subscript you're going to take. And then you might be like, I don't know. Like what's holding you back from giving me an answer? What's the issue with what you see in the question? They're all the same. They're all the same subscript. Which one's all the same? The potassium's all the same. Okay, good. That's one point. You're getting there. The potassium's all the same. But then, guys, earlier you were looking at subscripts because you were relating molecules to atoms. Yeah. Here you're relating element to element, potassium and oxygen. Okay. So I don't just need the subscript for potassium. That's one issue. What about oxygen? Any issues you see with oxygen? Because I need to get to the oxygen. Remember, I have the potassium right now. The oxygens have different subscripts. Good. So then it's like, what subscript are you going to take to relate the potassium to the oxygen? Okay, so the fact that you guys aren't able to give me an answer sort of implies that there's not one subscript that you can take because there's a bunch of different ratios. Would you agree? So the reason you're not able to pick an answer for me is because if there's different subscripts, there's different ratios, true or false? If there's different subscripts, there's different ratios, true or false? True. Okay. So then so you're getting on the right track. When I ask you these questions, I'm not looking for the answer straight away. This is the kind of stuff we deal with. We have to have these conversations because there will always be stuff you don't know in the exam. If there's different subscripts, there's different coefficients, which means I can't relate the potassium to the oxygen straight away. So if you tell me different subscripts, different coefficients, if you tell me different subscripts, different ratios, that means the different ratio is an issue. Yeah. The same subscript for potassium was actually a good thing earlier. Fair enough? Because at the start, you guys told me you can't give me an answer because potassium has the same subscript, so you're not going to know which one to take. But then now you're saying if there's different subscripts, there's different ratios. The different ratio is the issue. The different subscript is the issue. So we actually like that potassium has the same subscript. Yeah? But guys, you don't have to figure out the oxygen directly. what did I tell you? What did we figure out with one of the, which one was it? The earlier question that we did with the isotopes. Everything in the mixture has to add up to what? What percentage? Everything has to add up to 100. If you have things, if you have two components, you only need to know one component to figure out the other. If you have three components, you only need two components to figure out the third. Okay, so here, maybe I don't have to get to oxygen directly. All right, guys, what about sulfur? Does sulfur have different subscripts too, or can I relate them? If I can't go to oxygen, I'm gonna go to sulfur. That's the only other choice. So sulfur has the same subscript in all of them, which means the ratio is maintained. What's the ratio of potassium to sulfur in every single component of the mixture? 2 to 1, exactly. For sulfur, for potassium to sulfur, it's 2 to 1 the entire time. Okay, so let's make an extra note here for your notes. You can't do stoichiometry for a mixture unless the ratios of the ratios in every component are the same. So because it's 2 to 1 for the first component, 2 to 1 for the second component, 2 to 1 for the third component, it's always going to be 2 to 1 for the entire mixture. That's not true for the oxygen. So what that means is when you mix all of the different ratios for oxygen together, you're going to get an unknown ratio of oxygen to everything else when you mix it all up. That's not true for sulfur. So I'm going to go to sulfur first. If I can figure out the mass of sulfur, everything has to add up to whatever total I said. So I'll figure out the oxygen that way. So you currently have potassium. You're trying to go to the sulfur. 2 to 1. What are you going to do? Times by 2 or divide by 2? Guys, we're at potassium. We're going to the sulfur, yeah? 2 to 1. Divide by 2. Okay, so we're going to divide by 2 to get to the sulfur, which is half times moles of K, 1.5345. Oh, sorry. 1 on 2 times 1.5345. So how many moles of sulfur is there in all of this? Thanks, guys. 0.7672 mole. Okay. And then, guys, we said that if you can figure out two, you can figure out the third. But so the whole thing has to add up to whatever number I got for the mixture. Yeah. And then the number I got for the mixture wasn't in terms of moles though. The number I got for the mixture was in terms of mass. Okay. So everything has to add up to whatever the number for the mixture is. The number for the mixture is 100 grams, which is mass. So I'm not going to do it in terms of moles. I had to convert to moles to relate the different elements, but when I go to figure out how they all add up, I do that in terms of mass. Okay, I've already got the mass of the potassium. If I also know the mass of the sulfur, mass of potassium plus mass of sulfur plus mass of oxygen will give me the 100 grams. So I only did moles to relate the two elements. For me to get back to the mixture, I have to convert it back to mass. Yeah. So mass of sulfur, moles times molar mass, 0.7672 mole times sulfur in your periodic table, 32.07 grams per mole. So what's the mass of sulfur in all of this? $24. Some of you guys rounded off somewhere. 24.60. So some of you might have taken the number from the screen. Your answer is very close, but it's the tiniest bit off grams. So then the whole thing, guys, has to add up to the 100 that I said. So mass of K plus mass of sulfur plus mass of oxygen equals the 100 grams that I set. So mass of oxygen is 100 minus the potassium, which I set at 60, minus the sulfur that you guys got, which is a 24.6-ish. So what do you get for just the oxygen? 15.39. And then you round it off. The questions rounded off to 3 sig figs, which is 15.4. So remember, because we set a basis of 100 grams, your mass and your percentages are the same. Yeah, so 60% potassium was 60 grams. So then if you get 15.4 grams for oxygen, that's 15.4%. Yeah. So you can do if you want to 15.39 divided by 100 times 100, but that'll give you 15.39%. Okay. So that was why it was easy to set it at 100 grams in the first place. Yeah. All right. Good. Question 8. In an experiment to identify a group 2 metal, X 0.102 grams of X reacts with an excess of aqueous hydrochloric acid. The fact that they've told you it's excess means that the X is one's excess, one's limiting. Good. So guys, you don't have to check for the limiting reagent if they've told you A, that it's limiting, or if they've told you B, that something else is in excess. Yeah. Otherwise, if they don't mention limiting, if they don't mention excess, and they give you information for multiple reagents, you check for the limiting reagent yourself. This case, I don't have to, which is good. Again, they've asked you for whatever X is, and the information they've given you is for hydrogen gas. Relating different chemicals, you have to do it in terms of moles. In this case, guys, the information they've given you, temperature, pressure, volume, so PTV. You get given multiple equations for moles. What equation are you going to use here? It's a gas. In this case, you're going to use your PV's nRT, your ideal gas equation. So pick the appropriate equation depending on whatever they give you. PV is nRT, and then they've asked you want moles for hydrogen so that you can get to moles of X, yeah? So moles of H2 is PV on RT. You need particular units, okay? If you do pressure in kPa, your volume is in liters. If you do pressure in PA, your volume is in M3. Your teacher might have taught you other units. Use those if you like. If your teacher is nitpicky and prefers answers to be a particular way, P in pascals and volume in M3 is standard units. Yeah, they're SI unit. It's what people normally use. If they prefer kPa or liters, keep that in mind as well. Just whatever your teacher wants. Either way, you'll get the same answer. Yeah. They've given me pressure in kPa. So we'll go 99 kPa, which means for volume, I want that in liters. Okay, guys, 65 cm3 is 65 ml. Okay, so 1 cm3 is 1 ml. These are conversions you learn in maths class. So then if it's 65 ml, it's 0.065 liters. That's what I'm going to sub in. 0.065 liters. And then R is your ideal gas constant, which you either get given in the data sheet or you have memorized. What's the ideal gas constant? Mm-hmm. 8.314 joules per mole per Kelvin. And then temperature has to be in kelvins. In this case, they've already done it for you, 303 K. What do you get for the moles of hydrogen, please? 0.00255. Thank you. That's mole. And then, guys, the equation's balanced for you. For H2 and X, it's a 1-to-1 ratio, which means the moles are the same. So that's fine. And then this is asking you for whatever X is, which isn't a number, but we've done questions like this before. You know now that anytime the question's asking you to identify something, what's the quantity that you're calculating? What is unique for every formula? Whenever you get a question to ask to identify, what you're calculating is the molar mass. Exactly. So whenever they ask you for what something is, you're calculating molar mass. Okay, it might not be obvious because they don't ask you for a number, but you are looking for a number. So moles is mass on molar mass. So therefore molar mass is mass on moles. The mass was given to you in the question as 0.102. So molar mass of X, 0.102 grams divided by the 0.00255 that you got per mole. Then what is the molar mass of this unknown X? $39.93. Oh, grams per mole now. And then you have to check what element this matches the molar mass of. And guys, they've told you it's a group 2 metal. You don't need to check every box in the periodic table. You just have to check the second column. Which one does this match closest to? Calcium, which is B. Good. So you don't have to go looking for the whole thing. They told you it's a group 2 metal, which means you just look at column 2. Yeah. So your takeaway from this question, one of your equations for calculating moles is PV is nRT, only works for a gas. And if you get asked to identify something in your exam, what you're calculating is molar mass and seeing what it matches. Okay. All right. I want to show you a simple empirical formula question before we go on to something harder. Yeah. 17, Unix base is a monobasic amine containing 74.34% carbon, 14.82% hydrogen, and then nitrogen by mass. How many hydrogen atoms are in one molecule of Unix base? You want to know the formula and then figure out how many hydrogens there are. So this is the same thing as asking you for the empirical formula. They haven't asked you that directly in the question, but you need to figure out the empirical formula if you're going to see how many atoms of hydrogen there are in the molecule. Yeah, so we're following the steps for empirical formula. You guys already know, learn from the previous question, if it's a percentage, then you set a basis of 100 grams so that the mass of everything, 74.34 grams for carbon, 14.82 grams for hydrogen, 10.84 grams for nitrogen. Set any mass you want, but that's the easiest one to do. Ratios are in terms of moles, not in terms of mass. Ratios in a formula are in terms of moles. So I don't want mass, I want to convert it to moles. So moles of carbon first, 74.34. Who has the molar mass of carbon memorized by now? You've been doing this for ages. 12.01, good. 12.01 grams per mole. Tell me what you get for carbon. Who has the molar mass of hydrogen memorized by now? Come on. Okay, 1.008 grams per mole. Tell me what you get for hydrogen. And then last one, nitrogen. This one's a little bit trickier. You don't do it as often, but it's often enough. What's the molar mass for nitrogen? Okay, similar to carbon, off by one digit, 14.01 grams per mole. Hey, I got less people for the nitrogen one. What are your three numbers? So carbon, 6.189-ish. Hydrogen, 14.70, and then nitrogen 0.773. And then guys, empirical formula is the simplest whole number ratio. Okay, if I want to turn things into a nice whole number, a nice big number, no longer decimals less than one, then I want to divide by the smallest number. Yeah, dividing by the smallest number means every other number is bigger. So when I divide by the smallest, every other number will be a number bigger than one. Okay, so I'm going to divide all of it by 0.773. 0.773. So for nitrogen, you'll obviously get one because it's dividing by itself. What do you get for the other two? And it should round off to approximately a whole number. So you should get very close to like a 0.99. If it's like a 0.5, we'll have to convert it to a whole number afterwards. We're dividing by the smallest number and it just so happens to be 0.773. That's to convert everything into a whole number. So these should all be in ratio. So the 6 and the 14 and the 0.7 are in ratio. It's just really ugly numbers to look at. So if I can divide by the smallest number, I'll turn it into something that's a lot nicer, that's all. It should already be in ratio. I'm just expressing it differently. So hydrogen, so carbon 8 and then hydrogen 19. So your answer for this question is they've asked you for hydrogen atoms only, guys. So your answer is D, 19. But if the question was asking you directly to express the empirical formula, then you go, oh, C8H19 and a single nitrogen. Yeah. If they ask you for the formula directly, just put the number as the little subscript on the bottom right. Okay. All right. So this is your base case for an empirical formula question. What I want you to keep in mind is that generally speaking, empirical formula is the simplest whole number ratio by moles. Yeah. Your job, anytime you get asked about empirical formula, no matter how the question is expressed, you need to know bare minimum what you need to do a question and then adjust according to whatever the question asks you. Yeah. Bare minimum to figure out empirical formula is the moles of each element. However you go about doing that depends on the question. Okay, if they give you mass, you do mass and molar mass. If they give you concentration, you do C times V. Okay, it depends on whatever it is in the question. Yeah, so you need to remember your bare minimum and then adjust from there. Okay, so keep this in mind when we do this next one. Yeah, bare minimum, you're calculating the moles of each element. All right. Imogen, do you mind reading question 28 for us, please? After combustion with.
After combustion with excess oxygen, a 12.501 grams of petroleum compound produced 38.196 grams of carbon dioxide and 18.752 of water. A previous analysis determined that the compound does not contain oxygen. Establish the empirical formula of the compound.
Thank you. So, what did we say from the previous question? Anytime they ask you for empirical formula, you're figuring out the ratio of each element and what is that ratio in terms of? What is our job? This is a different question. Our job is to get moles, okay? Your job now is to help me figure out how we're going to get the moles, okay? So we don't know what the petroleum is. I'm just gonna go petroleum. After combustion with excess oxygen, so I'll put O2 here. And then carbon dioxide, CO2 plus H2O. Okay. So I'm gonna present to you the information in the question. You know that you're gonna have to get to moles somehow. And it's the moles of, did I say it's the moles of the compound or it's the moles of each element? Let's make a note here so that you can remember. Moles of what? It's the moles of each element. When you're trying to figure out empirical formula, you need the moles of each element. So keep this in mind because I'm about to ask you, yeah? This is your equation. And then they told you it's 12.501 grams of this. The carbon dioxide is 38.196 grams. And then the water is 18.752 grams. All right. You need to go in the exam knowing the bare minimum needed for each type of question and then adjust according to whatever unique question you get. You go into the exam knowing that if they ask you about empirical formula, you need somehow to find a way to get to the moles of each element. First of all, one criteria is moles, one criteria is element, yeah? Getting the element first is probably a good idea. Okay, it's like, what's the point of getting a number for moles if you don't know what element it belongs to? Okay, so let's deal with this one first. All right. What elements are you even looking for the moles of? What elements exist inside the petroleum? Can you lose elements in an equation? Can you lose elements in an equation? No, you can't. So guys, if it shows up on the right-hand side, it has to show up on the, if it shows up on the right-hand side, it also has to show up on the left. Okay? What elements on the right-hand side do you currently not see on the left and that therefore are probably in the petroleum? the carbon and the hydrogen. Okay. Now, oxygen's on the right as well, but they told you in the question that the compound doesn't contain any oxygen. Good. So you figured that out. Your two elements are carbon and hydrogen. Step number 2 is to figure out how to get to the moles of them. How are you going to get the moles of each element? Any hints, any guesses? I want a conversation. Like I told you, these questions are hard. When you know it's hard, I also know it's hard. Yeah. I'm not looking for the answer straight away. I'm looking for curiosity and a willingness to figure it out with me. Okay, good. So they've given you mass, which means you're gonna have to do mass on molar mass. And then I'm gonna challenge you as you go. Yeah, this is what I want. I want you to be curious. We'll figure it out as we go. Now, here's the thing though, guys, they've given you the mass of, let's say, CO2, yeah? Which means when you do mass on molar mass, what are you gonna get the moles of? Something else or CO2? I'll repeat the question. Yeah, good. They've given you the mass of CO2. So my question is, if you do mass and molar mass with that, what are you going to get the moles of? The CO2 or something else? That's the question. If you use the mass of CO2, you're going to get the moles of CO2. And we said that's not what we want. We said we want the moles of each element. Okay, you're on the right track. When I challenge you, you're on the right track. Yeah. If I don't question you further and I completely say something different, that's when you know I'm trying to redirect you. Yeah, so you're on the right track. Okay. So guys, when you do mass on molar mass with this, you're gonna get the moles of CO2. Remind yourself again, what elements do you actually want the moles of? Carbon and hydrogen. Guys, you currently, if you do mass on molar mass with that 38, you're gonna get the moles of CO2. You want the moles of carbon, you want the moles of hydrogen. Which one do you think you're more likely to get from CO2, the carbon or the hydrogen? That one's pretty obvious. The carbon, okay? Because carbon dioxide has carbon in it, yeah? You do the 38 grams divided by the molar mass, you're going to get the moles of CO2. How do you get the moles of carbon from that? How do you get the moles of carbon from CO2? How do you get the moles of C from CO2? We covered it in today's class. CO2 is a molecule or an atom. CO2 is a molecule. Carbon is a molecule or an atom. Carbon's an atom. Guys, you did it today. Molecule to atom. What are you doing? Yeah, Nova, exactly. Good. No, no, guys, you're going molecule to atom. What are you doing? What are you multiplying by? You're multiplying by the subscript. Good, thank you. So if I told you that you had 1 mole of carbon dioxide, how many moles of CO2 are there? Oh, sorry. If I told you you had 1 mole of CO2, how many moles of carbon are there? 1. If I told you you had 5 CO2s, how many carbons are there? 5. Good, because it's a 1-to-1 ratio. The invisible subscript on the carbon is 1, okay? You need to go into the exam with a bare minimum and figure the rest out based on what they give you, because the questions aren't always going to be standard, yeah? These are things that we build, these are skills that we develop over time. You can't do this for every syllabus dot point because there's too much, yeah? Okay. You need the moles of carbon. The moles of carbon on the left has to equal to the moles of carbon on the right. That's why we can relate the carbon in here to the carbon in here. Nothing can be lost. What is that? That's the law of what? Law of conservation of what? Nothing can be lost. Nothing can be destroyed. Law of conservation of mass. You can't lose anything. Yeah. So if you can figure out the amount of carbon on the right, that's the same as the amount of carbon on the left. Okay. So moles of carbon is moles of CO2, which is mass on molar mass. I'm gonna stretch it with this one, yeah? Anybody happen to have the molar mass of carbon dioxide memorized? You've done it enough times, come on. Or just do it in your head for me and pretend like you just memorized it. You know carbon, you know oxygen. No, you're not you're not supposed to calculate in front of me. You're supposed to give me the number and pretend like you had it memorized. Okay, now I know you just calculated it. Guys, molar mass of carbon dioxide, CO2. No. I'm gonna keep on giving you guys a chance. We're gonna do the hydrogen one as we go. Thank you. 44.01 grams per mole. All right. Ah, water's easy. I'm gonna get you to redeem yourself afterwards. Now, here's the thing though. To pop the carbon one in the calculator for me, we're gonna go with hydrogen. With the hydrogen, how many hydrogens in a water? There's actually two, yeah? So when you get the moles of water, timesing by two will get the moles of the hydrogen. Okay, so it's not always 1 to 1. So moles of hydrogen is 2 times the moles of water, 2 times water's 18.752 grams. Molar mass of water. Come on. Good. Oh, you guys calculate carbon dioxide better than this. What is easier? The numbers are smaller. 18.016 grams per mole. All right. What do you get for the two numbers? There shouldn't be any. Guys, you're timesing the hydrogen by two. Okay. 1, 7. And then the carbon one, 0.86789. And then now you're back at the same spot as the previous empirical formula questions. You've got the moles of both of them. You're going to divide them by the smallest number, 0.86789. Again, these moles should already be according to ratio. The only reason we're dividing by the smaller number is just to get it to a nice whole number. Yeah, so the ratios are easier to look at basically. What do you get for these two? Carbon's obviously 1 because that's the number you divide by itself. What do you get for H? Now, unless it's very close to a whole number, you can't round to a whole number. Yeah, so when I say whole number, I'm expecting like 0.000 or 0.99999. Otherwise, you're gonna have to give me like a point 0.3, point 0.4, point 0.5 or something, and then we'll convert it to a whole number afterwards. Okay, so when you get to this point, you get a like 2.398-ish. So the 98 is fine. That's big enough. I can round that off. So 2.398 will round off to about a 2.4. Okay. So let's figure it out as we go. This is too far in the middle, too close to a 2.5 for me to round off to anything. Yeah, I can't round this off to a whole number. 2.4 times 2 will give me what? I need to figure out the next whole number. 2.4 by 2 is quick maths. 2.4 by 2. 4.8 by 3. 2.4 by 3. You're going to help me figure out what the next whole number is. 2.4 by 3. 7.2. 2.4 by 4. And then 2.4 by 5? 12. Okay, so timesing it by 5 is the one that gives you the whole number, yeah? Empirical formula is the simplest whole number ratio. I need to get it to a whole number. So times both by 5. So guys, you only do this step if it's currently not a whole number, yeah? So carbon ends up with 5, and then hydrogen ends up with 12. Your empirical formula, C5H12.